Good morning and welcome to today's lecture. As you can see, this is lecture number 17 in one of the most interesting topics, radiation. As I've already told you, these questions on this topic can appear in mains, JEE Main, obviously, definitely. But they are more likely to appear in JEE Advanced. And the questions from this chapter, they look very confusing because this particular topic, radiation, I mean, everyone covers conduction very nicely. All sorts of questions are there in conduction. We have also solved so many questions in conduction. Everyone does conduction very nicely. But when it comes to radiation, everyone is in a fix because we don't understand this radiation and it becomes difficult to solve questions because we have not understood it. So, we must do this topic carefully because if a question comes, and I have told you it will be a sure short question that comes, you can easily solve it. So in the last class, what we were discussing, do we remember what was the last topic that we did in the last class? I think you got disconnected in the last class. Is that so?
Emission. Radiation emission.
What? Variation in?
Emission.
Emission. We were, I think, discussing the various terms or terminology of radiation. We had seen what are the terms that we might encounter in radiation. Do you remember what are the terms that we will encounter here? We had talked about certain terms that will come, and I told you this chapter is all about understanding those terms. If you understand those terms, you will see the questions are pretty damn simple, whether it's from JEE Main or Advanced or wherever. What were the terms that we did ask us? Fatafat, tell me. Do we remember those terms? I guess not. Well, dangerous sign again. But still, what to do? So these were the terms that we discussed in the last class. Just have a quick recap. Because if we forget this, then again, when we are going to go ahead, we are going to get more confused. The first one was reflectance or reflecting power ratio. Total power reflected, total energy reflected divided by total energy which has fallen. Transmittance or transmitting power, energy transmitted divided by energy falling, small t. Absorptance or total absorptive power, small a, energy absorbed divided by energy fallen, and a plus r plus t is equal to 1. We had also seen what will happen if the body is a perfect absorber, perfect reflector, and so on. Then we had seen something known as spectral absorptive power. Yes or no? Spectral absorptive power for a particular wavelength, how much energy is absorbed divided by how much energy is falling for that particular wavelength. As I told you, when we talk about radiation, the range of radiations that fall on a body or that a body emits starting from 0 and it goes till infinity. Then we saw what will happen when a body which is at temperature more than 0 Kelvin, it is going to emit radiations. We call it emission. Then we saw emissive power, total energy per unit area per unit time. Yes or no? Did we see it or not?
Yes, sir.
Then we saw spectral emissive power, and that was the last thing that we did. Now let us begin today's class. And how are we going to begin today's class? Well, we begin today's class and we try to figure out the remaining terms. As I always told you, this chapter is all about remembering terms. And the next term that is going to come again I told you some terms are in small letters and some terms are in capital letters. Here comes the next term, which is known as emissivity. And as you can see, this is denoted by small e. What was denoted by capital E? What was capital E? We have seen this capital E. You can see capital E here as well.
Emissive power.
Yes, capital E was emissive power or emissive power. And this is small e. Now, what is this small e? Now, in this small e, what do you see is something known as E black. Now, when I say E black, I must first tell you what is E black. To understand what is E black, we must understand what is the next term, which I think we were doing this in the last class and then your network got disconnected. So the first thing that you must understand is what is a black body, or for that matter, a perfectly black body. Anyone has any idea about what is a perfectly black body? Kali body in Hindi. Black body.
No, sir.
Never heard about black body? Okay. What is a black body? You might have heard about something which absorbs everything that falls onto it. If you can create a body like this, you can call this a black body. Please note it down if you are there. Again, this is taken from your notes, but if you note it down, you will remember it. What is a black body? A perfectly black body is that which absorbs completely radiations of all wavelengths incident on it. So basically, it does not absorb radiation of a particular wavelength. It will absorb everything that falls onto it, something like a black hole. Now, if you have heard about black hole, nothing escapes the black hole. Even light cannot pass through it. Even light falls on inside the black hole, it will get captured, something like that. Not exactly a black hole. Black holes are there in very far from us universes, but we can create almost a perfect black body on Earth. It's not very difficult to create it. So if we have a body which can absorb everything that falls onto it, all radiation that are falling onto it are absorbed by this body. A perfect absorber, I must say, if it is a perfect absorber, instead of calling it as a perfect absorber, we can call it as a perfectly black body. T is 0, R is 0, and the value of A is 1. Do we understand this? I have written this. What is a perfectly
Yes,
black
sir.
body? A perfectly black body is a body that absorbs everything, whose absorptive power or absorptance is 1, whose reflectance and transmittance is equal to 0. That is known as a perfectly black body, and this is the simplest example of a perfectly black body. We call it the Ferri's black body, and this is how it is constructed. I have a spherical space, and then I line it with some materials which are absorbing. Then I create a notch over here. Why is this notch created? Whatever radiations are falling, after falling on this notch, they get dispersed, and then after multiple reflections, if there are reflections, no radiation will come out of this body, and this becomes a perfectly black body. It has a very, very small hole. This is that very small hole. Whatever radiations go inside this body through this hole, they will never escape out. This is known as a Ferri's black body. Do we understand this? So this is a simple example of a black body. This is known as a Ferri's black body. Now, since we have understood what is a black body is a perfect absorber of thermal radiation. Whatever radiations fall on that body, it will completely absorb everything that falls onto it. Now, we can come across this term and probably will now make more sense out of it. Instead of capital E is the emissive power, total emissive power. If I write E lambda, it becomes spectral emissive power. I hope you understand this. So E is the total emissive power. E black is the emissive power of a black body of same dimension, same size, same shape. So for example, if this is one of the bodies, its emissive power is E body, then I create a same body, same size, same shape, and I make it a black body. We call that its emissive power of the black body. What is the emissivity? How do we define the term emissivity? Emissivity is again a ratio. It does not have any units or dimension. So this question can also come in units or dimension. Emissivity. What is emissivity of a given body? Emissivity of a given body at a given temperature. Why this temperature is coming? Because energy depends on the temperature. Whatever thermal radiation this body is emitting, it depends on its temperature. Do we remember this? Do we know this? Yes or no?
Yes, sir. Yes.
We know this, that the radiation this emits depends on its temperature. Yes or no?
Yes. Yes.
Right. So if I change temperature, the emissive power is going to change. We'll see that in the coming class, maybe today only. So emissivity of a body at a given temperature is the ratio of the total emissive power of the body. You can write it E practical or you can write it as E body to the total emissive power of a perfectly black body of the same size, same shape, same dimension at the same temperature. So emissivity E will be emissive power of any body divided by emissive power of the black body of same size, same shape, same dimension, but it is black body. Do we understand this? The difference between emissivity, which is small e, and emissive power, which is capital E. Remember, this chapter is all about understanding definitions. If you understand definitions, you would be able to solve problems. And we'll see the problems are pretty damn simple once you understand the definitions. Have you done this?
Yes, sir.
Now, for a perfectly black body, the value of emissivity or E will be definitely 1. But for practical bodies, emissivity will always lie between 0 and 1. If emissivity becomes 0, that means this emissive power becomes 0. It is not emitting at all. If emissive power is very high, it is same as the black body, emissivity becomes 1. That means it is a very good emitter. Do you understand this?
Yes, sir.
Emissivity, simple terms, simple term, and this simple terms makes a hell lot of a difference. Now, if we have understood this, what we will do, let us see if you can solve this question. And again, as I told you, questions from this chapter come in JEE, and when I say JEE, I mean JEE Advanced. This is a problem that came in one of the screening papers of JEE. An ideal black body, let's see if you can do this. An ideal black body at room temperature is thrown into a furnace. What will be observed? Initially, it is the darkest body, and at later times, the brightest. It is the darkest body at all times. It cannot be distinguished at all times. Initially, it is the darkest body, and later, it cannot be distinguished. Again, we cannot guess. We must know the answer, otherwise, we lose the chance. How will you solve this question if you had to solve it? Again, you must understand that whatever question comes in a JEE, it will not be
Initially,
straight.
sir, initially it is darkest body, and later it's brightest. It comes brightest.
What makes you think so? Option is D. What makes you think so?
Option A.
Okay, option A. Initially, it is the darkest, and at later times, the brightest.
Yes, sir.
Okay. Chalo. I just gave you this question so that you understand how questions are framed in a JEE. We will be solving this, but right now, no, because you need some more information or you need some more knowledge before solving this one. So once I get you that information, then we will get back and solve this one. I'll just give you another one. First, the questions are pretty simple. First, solve this. Transmission power. Now see, I've told it to be transmittive power. They can use different terms. Don't get confused. The transmission power of a surface is 1 by 6 and the reflective power is 1 by 3. What will be its absorptive power? Let's first solve this. I'll give you more information before solving that question. And then I am sure you should be able to solve this question that I showed, the JEE Advanced wala one, and gain more confidence. Yes, so how do you do this?
1 by 2, sir.
It's very simple now. How to do this? Shall I tell you? 1 by 6 is the transmittive power or T. 1 by 3 is the reflective power or R. A plus R plus T has to be equal to 1. So absorptive power will be 1 minus 1 by 6 minus 1 by 3. Whatever you get is your answer. I think you get 1 by 2, right? No, whatever. Chalo then. We are done with this. Now let us do this topic and then we'll go back to the question and see how that question pans out. You might need more. See, whenever a question comes in any topic, it may not mean that whatever you have learned is small thing that may be able to solve that question, because there could be other complication in the question which can only be understood once you understand the entire topic. And JEE Advanced is just like that. Wherever a question comes, it tests your understanding of the entire topic. To get to the next part, let us see something which is known as Kirchhoff Law. Have you ever heard about Kirchhoff Law? You must have heard about Kirchhoff Law. I think we discussed it in the previous class when we were discussing nodal theorem. We heard about Kirchhoff Law. Yes or no? Yes or no?
Yes, sir.
But then that was Kirchhoff's law for electric circuits and electric currents. We have two types of Kirchhoff law. One is known as what? One is known as Kirchhoff's current law, junction law. Incoming is equal to outgoing. One is known as Kirchhoff voltage law. If you move in a loop, the difference in voltage is zero or there is no change in voltage. Here it is Kirchhoff's law of radiation. And what is the Kirchhoff's law of radiation? Please remember it, and it will give us a very, very good result. And what is that good result? The ratio of emissive power to absorptive power. So what is emissive power for a body? We can call it as A. Yeah, we can call it as capital E. Yes or no?
Sir.
Emissive power of a body, you can call it as capital E, divided by, he is saying absorptive power of the body. So I write it absorptive power A of this body is same for all surfaces at the same temperature, and it's equal to the emissive power of a perfectly black body. The ratio of emissive power, if this is, if I just go back, this is a body. It has some emissive power. It's going to emit radiation because it is more than 0 Kelvin. It is going to emit. At the same time, it is also absorbing radiations which are falling on it. If I find the ratio of this emissive power with absorptive power, remember emissive power has got dimensions. Absorptive power does not have dimensions. So we are dividing a quantity which has got dimension to a quantity which does not have a dimension. So I should not call it ratio, but this is how it is said. So I'll just keep it that way and not change it. So again, going back to what I was saying, the ratio of emissive power is not actually a ratio, but it is how this Kirchhoff law has been written, so I will not change it. The ratio of emissive power to absorptive power is a constant for all the bodies at a given temperature. This is a constant. It does not change. And this is equal to the emissive power of a black body. You can also divide it by the absorptive power of the black body, but absorptive power of black body is how much?
Perfectly black body.
Yes. When I say black body, it's a perfectly black body. There is no imperfect black body. Yes.
1.
1. So if I divide E by 1, I still get E. So you don't have to divide it. So emissive power of any body divided by the absorptive power of any body will be equal to the emissive power of the black body of the same dimension at the same temperature. Do we understand this? A very important statement that you must remember. A very important statement that you must remember. Ratio of, it's not a ratio of emissive power to absorptive power is always constant, and that is equal to the emissive power of a black body. Do we understand this?
Yes, sir.
Absorptive power of black body is 1, so even if you divide it by 1, doesn't make any difference. Now if I just jumble this entire thing up, when I say jumble this entire thing up, what do I mean? I bring this emissive power of the black body here, and I take this absorptive power of the black body here. What will I get? Jumble this up. So what will I get? I hope you understand what I'm doing here, right?
Absorptive power of black body.
So I will say I will get emissive power of the body divided by emissive power of the black body. Yes or no?
Yes, sir.
That will be equal to the absorptive power of the body. Yes or no?
Yes.
But as soon as you see emissive power of the body divided by emissive power of the black body, this is now a ratio. This is now a ratio. Emissive power of the body divided by emissive power of the black body. What does this ratio give you?
Absorptive power of body.
What does this ratio give you?
Absorptive power of body.
That is what you have just learned now. What did you learn 5 minutes before? Emissive power. Yes?
Emissivity.
It is emissivity, small e. And a very, very important conclusion we have got. Surprise, surprise. Absorptive power of the body is equal to the emissivity of the body. Dun, dun, dun. That means both things are same. So when I'm saying absorptive power of the body, I'm actually referring to its emissivity as well. That means if a body is a good absorber, it is a bad reflector. We know this. Good absorbers are bad reflector. Good reflectors are bad absorbers. But here we are not talking about reflection. We are talking about emission. If this is a body and it absorbs a lot, it will also emit similarly. If the absorptive power is 0.5, emissive power or emissivity, not emissive power, emissivity, which tells us how much it is emitting, it is also 0.5. Good absorbers are good emitters. That is what Kirchhoff's law states. Do we understand this, what I am trying to make?
Sir.
What? Repeat it.
Good absorbers are good emitters.
But very bad? But very bad?
Reflector.
But very bad reflector. This is what you must always remain. So now your knowledge of these absorbers and emitters become complete with this discussion that good absorbers are bad reflectors but very good emitters. Do we understand this?
Yes, sir.
What do we understand? Good absorbers?
are good emitters and bad reflector.
Good absorbers are good emitters, but they are bad reflectors. And that is how we summarize this entire thing. Who is the best absorber? Who is the best absorber of them all? Mirror, mirror on the wall. Who is the fairest of them all? Who is the best absorber? Mirror, mirror on the wall. Who is the best absorber of them all?
What? Once again.
Which body is the best absorber?
Black body.
Black body. The best absorber is a black body. Kali body. Mirror, mirror on the wall. Who is the best absorber of them all? Black body, whose absorptive power is equal to 1. We know it. Emissive power is equal to 1. They have to be same because E is equal to A. Do we understand this?
Yes, sir.
Black body is the best absorber, but at the same time, it is also best emitter. So we call it the ideal radiator. It is the most ideal radiator. Do we understand this?
Yes, sir.
But it will be a very, very bad reflector. It will not reflect, but it will be the best emitter. Do we understand this? So
Yes, sir.
Kirchhoff law is basically telling us this entire thing, and it is giving us a very beautiful result. And the result is absorptance or absorptive power is same as emissivity or emissive power. This is not emissive power. This is basically emissivity. Do we understand this? Can I have some reason that we understand this?
Yes, sir.
This is all about Kirchhoff law that we must understand, and there can be questions which are asked on this particular topic. To understand it, the questions are going to be pretty damn simple, and I can assure you that. What I'm going to do is see if I have question on Kirchhoff's law. I have a question of IIT screening. Okay, let's see if we can do this. I will have to shift the page here. Okay, but before going on to the question of JEE screening, we have one question remaining, which is of the black body. What happens if I put black body in a furnace? We'll come to that. Don't worry. I'll come to that, but we'll do something else. Then we'll go back to that. Now, we talked about absorptive power of the body, but we also talked about something known as the spectral absorptive power. Do we remember this?
Sir?
Spectral absorptive power. Do we remember spectral absorptive power? This A that I've written, that was the total absorptive power. We have also seen something known as the spectral absorptive power. Yes or no?
Yes, sir.
How do I get the spectral absorptive power from the same concept or same formula? So basically, if I divide spectral power of the body and I divide it by the spectral power of the black body, we normally don't do this because a black body has the same thing. We will get the spectral absorptive power of the given body. Do we understand this?
Yes, sir.
So this is how you can find the spectral absorptive power of the body. This is how you can find the total absorptive power of the body. Remember, these terms may get very confusing, and that is what the advantage they try to take in the JEE advanced paper. That is why you might not have question for this in JEE Mains. This is strictly a topic based for JEE advanced. And what I see, the students at the back, they are engaged into something. I don't know what. Are we there? The last benchers in the class? Can I have some reason that we are in the class and doing and studying physics only? Okay, good. So this is spectral emissive power. Ratio of spectral emissive power of the body divided by spectral emissive power of the black body will give us the absorptive spectral absorptive power. Now, the next topic, and again a question of this has come in JEE. So we will see this, but let us see if you can solve this question, which is based on your Kirchhoff's law. So this is again a question, and I told you most of the question that you will see in this chapter will be it's a variation of temperature, and you will not be able to find out the variation of temperature right now because I'll have to teach you something else before that. So I'll just teach you something else, then I will come back to this. And the next thing that I'm going to teach you is this. And then we will solve all the questions together. Okay. Distribution of energy in the spectrum of a black body, Kali body. The other way in which I normally write it is the spectral distribution of thermal radiation. This is how I define this particular topic. Spectral distribution of thermal radiation. Now, what do I mean by this spectral distribution of thermal radiation? And questions on this straight away have come in JEE more than once. JEE Mains many times, because this is one topic which normally people do, but they don't understand the significance of this topic, because the next time this question comes, it will not be a straightforward. Probably you will get a multiple choice question on this. So you have to understand this diagram very carefully, this graph very carefully, for you to make any sense of this graph, else this becomes useless. Now, what I have drawn here on this diagram, I hope everyone can see this diagram. I have drawn E lambda on the y-axis and lambda on the x-axis. Do we see this?
Yes, sir.
Or shall I make it bigger?
Bigger.
We'll make it bigger. Let us see if you can make more sense out of this. Oops. I think this will do nicely. So I have drawn a diagram, and this is very nicely drawn so that we understand the things that we have to understand from this diagram. I have drawn lambda here and I have drawn E lambda here. So I have drawn a graph between E lambda and lambda. Yes or no?
Yes, sir.
Now I have previously drawn the same graph as well between lambda and E lambda. At the back, are we there? Whosoever is sitting in the back, why don't you come at the front so that I can see your face, bacha? Come at the front. It becomes very difficult for me to see you. Come at the front. That's better. Good. Okay, I have drawn a graph between E lambda and lambda. What does the graph between E lambda and lambda give me? When I drawn that graph between E lambda and lambda, what do I get from the... Yes?
Spectral emissivity and wavelength.
I had drawn the graph between E lambda and lambda before. I hope you remember the question. What does the graph between E lambda and lambda give me?
Total emissivity and
Not emissivity, beta. You are confusing the terms. If you confuse the terms,
emissive power.
yes. Don't say emissivity. Emissivity is the ratio, beta. Don't get confused. That's why I'm telling you. The only thing that will confuse you in this chapter is the definition. Don't get confused. Okay. So if I find out the area, I will get the total emissive power. Yes or no?
Yes.
Okay. So how do I get the area? I just find this area, right? Dung from 0 to infinity, right? So E will be equal to integral from 0 to infinity E lambda d lambda. Yes or no? We understand this, correct?
Yes, sir.
Good. The first thing is, now here I have drawn it at 3 temperatures, T1, T2 and T3. Now, with whatever I have told you till now, and I have also written it in red, which I am going to rub right now so that the diagram becomes more clear. Now there are 3 temperatures given to you. What are the inferences that you can draw? If you can draw your own inferences, I don't have to teach you anything, because then my job is done. What are the inferences that you can draw from here? What are the inferences that you can draw? Remember, this is T3, this is T2, and this is T1. This is the graph between E lambda and lambda. What is the first inference that you can draw? What is the first inference that you can draw? Well, again, I think that the problem is there with the power. So we'll continue this class in the next class. Take care. Have a nice day, beta.